This is
Do I have them on
578.
579?
Alrighty.
Yeah, you kidding? 578 was so last week. All right, I'm gonna say hi to everybody. Hello to. Actually, you know what? I'll give you a couple minutes. There's not enough people yet.
And I actually see how I can fix this hellscape lighting that makes it look like I have no nose. One moment.
Live. So we were just talking about this beforehand. We just crossed the 10,000 mark on YouTube subscribers. Woo! 10,000. Yeah, that's way better. Yep. Nope. No, whatever you had before. Before you
That is
turned on that
entirely the
light,
wrong
whatever that
direction.
light was, turn that off again.
Wait, that was the wrong ear. Can't hear you.
So no. So whatever you had just before, it looked great. Yeah, that.
Yeah, I'm just trying to add a little bit of orange to that. There.
Okay.
I'm gonna stop.
Perfect. That looks great. That looks absolutely perfect. It's sort of, you know, lower brightness.
Yeah,
So
I turned off the overhead fluorescence and turned on my studio lights, which makes sense.
hold on. So you're saying that you had bad lights and good lights, and it just occurred to you now to turn off the bad lights and turn on the good lights?
Last week I only had the good lights turned on. This week I was being stupid and then I caught myself.
Okay. Okay. All right.
I just didn't adjust the settings enough last week.
That's but you seem to like press a button from your were you using it from your phone or something? Were you controlling the
I'm controlling it off my computer. So like I can
what?
go zoom.
What
That's actually
sorcery is this?
it's Elgato sorcery. So zoom, zoom, zoom.
That's incredible. Oh my
It's
god, I
it's
totally want to
very
do that.
exciting. Yeah, it's so this is gonna sound nerdy even for me, but I fight an ever going battle against lighting.
Yeah.
And when John Oliver started recording from his whiteness at home, he was perfectly lit and wearing glasses.
Mm-hmm.
So I could see the source of his lights in his glasses.
Yeah.
And then I went down the rabbit hole of what matches what is in his glasses. And it appears to be the Elgato lights. I just don't have all the reflections, and
Yeah.
dark hair plus red shirt plus dark
Still.
chair gives it a
Elgato.
lot of effort.
Elgato lights. Okay.
Yeah, they're really good.
That you can control.
Hmm.
Neat. Okay. Cool. Those are gonna go on my list.
And their tripods are like the best tripods ever. They just don't go as short as I'd like.
Yeah, I've got like some cheap ones. Um, okay. Yeah, I've got like some cheap lights that I bought. They're pretty good. They're
Yeah.
I mean they're LED panels um, that I use.
These are LED panels. They're
Yeah,
just
yeah, we
high
use them
quality.
for all like people love the lighting that we do for our outside videos. And we just have these lights that we put on tripods that they're a
Yeah.
light panel. They've got I forget like 60 LEDs. They're great. They're amazing. I mean, I really can't complain with what we've already got. But I would like to make it better just in the studio. In the studio where I can just flick a switch and the lights are go. It's
Yeah.
perfect, right? That's what
Where
you
where
need.
where I get myself into issues is depending on where I am in the room, I need these different sets of lights.
Yeah.
And it's just oh shoot, I need to click these things right
Yeah.
now. Stella.
I'm going to say hi now to people. Hello to Andy Cowley, Aaron C., Ben Kalo, Bill Smith, Corey S., Gordon Dewis, Graham W., Guido Bibra, Harry M., Herrick Bo Anderson, John Seffield, Jorn Albert, Caillou Wen, Larry Beckham, Lillian Brennan, Maria Kobetz, Mark Sheeran, Naked Hand, Nancy Graziano, Nolan DeSanto, Paul Disney, Paul Gracie, Sergusi, Side MT, Steve Highstand, Stuart Foreman, Subject Line, Did you want to do, and Zappan. Hey, everybody. Did you have some people to say hello to over on Twitch?
Oh my goodness. Yes. Yes, I do. I
I can
just
do
need
that
to
too.
find the correct window. So,
Hello, Astro YYZ and Trey Harmon and Beth Johnson.
all
It's
right,
it's
he's
a
got it.
it's a timing thing. Well, no, I don't have that, but the people are like, how come you didn't say hello to me? YouTube only shows us who commented within the last 5 minutes. So you have to comment, and you have to comment within the 5 minute window of when I start. So somehow organize yourselves all together to comment at the same time. That's how to do it.
I approve of this. So I don't have those comments to rely upon, but what I can say is hello AEU AAYE. You I don't know how to say your name. Comrade Two Face, Hodor, Ironheart, Limp Rimble, Lurks, Poltergeisty, Punk Junk and Jazz, The Command Prompt, Third Rock Astronomy, Tom Van Scooter, and Zine. Hello over on Twitch.
Right on. And so people caught right at the beginning, we crossed the 10,000 mark on subscribers on our YouTube channel, which is kind of cool.
It is. It's very cool.
I think we only need another 90,000 before we get our silver play button. We just need to get 10 times as many to get a silver play button. Although, I mean, I already have one, so humble brag. So let's, if you're wondering what it is that you've stumbled into, we're going to record a live episode of Astronomy Cast. We're going to take some random number of minutes that is just purely my whim, and then we will finish the episode, and then we will move on and answer your questions about space and astronomy, or I don't know, life on Venus for 30 minutes.
And I am just pulling up those of you who support us over on Patreon. First of all, you are awesome. Second of all, if you donate at the correct level, we thank you at the end of the episode, and you can include pronunciations for your names.
You sure can. It would be, Pamela would really appreciate it.
Yeah.
Ben Kayla says he'll send us a cardboard play button. Perfect.
All right. All right.
Bronze, yeah.
So I'm just getting up the names of the people I need to thank at the end of the episode.
Okay. So Zapfen saying, get more of your listeners to subscribe on YouTube. It's actually the opposite. I would prefer that people who watch us on YouTube subscribe to our podcast, because one, the podcast, that's a distribution channel that we completely control. You subscribe, and then when we release new episodes, you get the episode. YouTube is a capricious, fair weather friend that sometimes sends people to our videos and sometimes hides us when it wants to promote flat earth videos instead. So, all right. Are you ready?
I am just now inverting all of the white windows that I have opened so that I stop there. That's much better. All right.
All right.
I am now ready to find where I hit the record button. There it is.
All right.
Ready?
I press record.
I am recording.
Here we go. Astronomy Cast, episode 579, White and Black Dwarf Stars. Welcome to Astronomy Cast, our weekly... What are you...
I'm using the wrong mic.
No.
I have no clue why it changed mics on me. I'm sorry.
Yeah, I have like 17 audio devices on this computer.
Yeah, I was just looking at it and I'm like, that waveform is not the correct waveform.
The fact that you could just tell, just look at the waveform. That's awesome.
You can't?
Yeah, no, I totally can too. Yeah.
Okay. Dear Audition, why did you decide you didn't like this mic anymore? Why? Why did you do this to me? One or more files are actively processing jobs. Please cancel these. I don't know what other file you have open, you
Audition?
stupid thing.
You're not using Audacity anymore?
No, it doesn't run on the latest version of OS X.
Of course not. Why would it?
Okay, audio hardware. Yeah, it jumped over to using my default microphone. like the system default in the computer. Silly software.
This is just the best. This is just thrilling content.
I'm sorry.
Lillian Brennan says the Earth can't be flat. Cats would have knocked everything off of it by now.
It's true.
Science. That's just
Okay,
science.
I am ready to go. Are you ready?
I'm ready.
I am pressing record and I
I
have a healthy.
a good waveform?
Yeah.
Okay. Here we go. Astronomy Cast, episode 579, White and Black Dwarf Stars. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Doing good. Boy, have I been talking a lot about life on Venus, though. That's my life. That is the new reality, is just talking about life. How is the life? What could else be making the life? But the part that I love is the responses now that there are some cool missions in the works that people are thinking of
Yeah.
to send. I've seen a couple of really great ideas. Now we've got people have something very specific to look at. So hopefully we'll be able to follow up in a couple of years with some cool missions to go to Venus.
I I hope so. It's the thing that really frustrates me is I know the time scale of going from thinking about a mission to building and sending the
Yeah.
mission. And it's like I want them to go figure this out while I'm
But the
alive.
good thing is that Venus only takes a couple of months to reach. So it's not
I
like
know.
Saturn
I know.
or Uranus, right?
Mercury.
Yeah, Mercury's a tough one to get to, but hopefully we'll get some answers. We'll get some answers for you, everybody.
I hope so.
Now I've got some bad news for you though. Stars die. At
They
some point
do.
in the next few billion years or so, our sun is going to start heating up, using up all the fuel in its core, and then eventually die, becoming a white dwarf. It'll then slowly cool down to the background temperature of the universe, becoming a black dwarf. Let's learn about this fascinating process. What's the time scale? All right, first, why is the sun dying? I mean, we're all dying,
Well,
we're all born and then we're all dying. So why is the sun dying?
right. Ultimately it's just going to run out of energy. So the way that stars shine and support themselves is deep in their core. They're undergoing nuclear reactions. Now, exactly where in the core depends on the stage of evolution. Initially, when a star turns on, it's burning hydrogen. It's going through the proton-proton process, and all the light that is generated during this fusion, because when the particles come together, they release energy as they fuse into something new. And that energy pushes out against gravity, supporting the outer layers of the star.
And eventually
Now,
it runs out of fuel in the core.
yeah, so it's eventually going to run out of hydrogen in the core. The star is going to go through different changes in luminosity, changes in color, changes in size. It's going to end up burning hydrogen in a shell. It's going to end up burning helium in the core. All sorts of different things are going to change over the life of a star. And what all happens depends on the mass of the star. If a star is big enough, it's actually going to eventually get to the point that it has a heart of iron. And it turns out that when you try and fuse two iron atoms together, they say, sure, you can do it, but you have to give us the energy to do
Right.
it.
No free lunch anymore.
No free lunch anymore. And since trying to fuse these heavier elements doesn't release energy, the star doesn't have anything to push back against the fight with gravity. And it collapses down in this moment that it's no longer producing enough energy. And this is where things get interesting.
Now that's for the stars that are bigger than our sun, right? But for stars that are the mass of our sun, they don't have that catastrophic end. They just have this quieter cool down end.
And this is where physics can get interesting because it turns out that stars that are 10 solar masses and less undergo varying amounts of mass loss. And we're not always sure how much, in fact, we're never sure how much mass a star is going to lose. And over its lifetime, that 10 solar mass star may end up, once it's done bloating off its outermost atmosphere, as something only one solar mass in size. It can lose 9/10 of its material.
So, sorry, what's the
During,
mechanism that's actually causing that material to be lost?
so you have two different things that happen. The first is regular everyday solar winds, like what we're experiencing with our own sun, where the sunlight, as it pushes out, interactions with the outer magnetic field of the star. You have both things gradually getting carried off all the time and things getting ejected through coronal mass ejections, solar flares. And all of this is carrying particles, only atoms, electrons, small bits of matter, but still actual matter is getting carried away from the star. And the rate at which the star is able to lose mass through mass loss like this, through solar winds, is variable over its lifetime. And elder stars and the most massive young stars are the ones that give off the absolute largest amount of
Right.
mass.
And so once a star is done blasting off all its mass, once it's gone through this process of turning into a red giant and then multiple times sometimes, right? They'll blow it out and then shrink back down and then blow it out and then it's done.
Well,
And
and
it,
here by done, it's more a matter of it's like, I'm just going to let my outer atmosphere drift away. I'm just
right.
going to exhale it. And this is planetary nebula formation. And here it's just a matter of the light that the star is generating at this point and the size of the star make gravity just not quite as strong as it needs to be with those outer layers of the star.
I don't know if you saw a piece of research just came out like just a couple of days ago now that astronomers have been able to essentially tie down the shape of every single planetary nebula based on just the planets and any binary companions that are orbiting the star. So the different shapes now are
Yeah, I would have
entirely
phrased it
caused
differently.
are caused by the variations are caused by the interactions with whatever's orbiting the
Yes.
star.
And they haven't actually gone through and identified every planetary nebula in existence and matched it with their computer models. But what they figured out is the variations from having stars in various binary systems, stars in various solar system configurations, and stars pretty much on their own. By tweaking all of these different interactions, you're able to create the nearly infinite diversity of shapes, including all of the nested shells and things that we see with planetary nebulae.
Yeah, yeah. It's kind of cool though that planets can help make planetary nebulae.
Oh yeah,
Yeah.
and this is your standard reminder that the name Planetary Nebula has nothing to do with planets.
Except now it does.
Well, fair. The name itself, however, is
Yeah.
based on the fact that so many of these nebulae look like gas giants. The Owl Nebula through a telescope looks like it's another gas giant.
Yeah. Um, so then the planetary nebula blows off, and you are left with a star, but it's not like the kind of star that we were familiar with for the entire time that we've lived here on the planet.
And this is where we have to go back to, is it a star really?
Well, so what
Because
is it? What is left? What
so
is the remnant?
it's a core, it's a dead core, it's an ember. The basic definition that we have of a star, which is what allows us to say that brown dwarfs are temporarily stars, is you have to have that nuclear fusion going on that is generating energy. With a white dwarf, you have the core of a former star that is no longer generating energy, that is sitting there going, hi, I would collapse except for electron degeneracy pressure. The ability of electrons to go to other electrons. Do not get too close with the Pauli exclusion principle.
Right. This is our atom.
This is, yeah. So essentially a white dwarf star says, okay, electrons, align, and they line up according to the Pauli exclusion principle in all the allowed states, forming as dense an array as they can, pushing back against gravity.
Right. And we've talked about if you have a more massive object, then gravity can overcome that and force the whole thing into a neutron star. But today we're talking about the stars that don't quite make it.
Yes. And so with these leftover cores, they start out with a temperature at the surface of like 10 million degrees. They're
Wow.
radiating their light in the ultraviolet. It's the core of a
Right, right, right. Well,
star.
so let's just stop for a second because when you think about like a star like the sun, like the surface temperature of the sun is like whatever 5,700
Yeah.
Kelvin, and so that's hot, but that's not millions of degrees hot.
Yeah.
But when the sun has been running this fusion core down in the middle of it, and then it blasts off all those outer layers, and now, like, is it literally the core of the star is now just revealed to space,
Yes.
and it's
Now,
and it is millions of degrees hot.
and so the inside of the star is consistently at this 10 million, but that surface is it's going to drop down to 150,000 Kelvin as it radiates. Now, here's the thing though, is we have a pretty much solid object with a very small surface. This is your standard reminder that a sphere has a surface that is the minimum surface you can have for the amount of stuff inside of it, which means that it's not the most effective at radiating away heat.
Right. So so
So,
so sorry. So it's like because it's got this nice spherical shape, because it's holding in its atoms in the tightest possible configuration, like a bubble, right?
yeah,
It holds in the amount of air that's inside of it. It has a really hard time getting that heat out into the universe. But if you like took a knife and sliced open a little, took out a little piece of pie
10
from
million degrees
a 10
inside.
million degree, yeah, what would it be? What would you be holding if you could just like pull it out of the white dwarf?
Something denser than anything that you can generally imagine. We don't have material like this on Earth. You might be able to create it in a lab if you spent enough money, but your average person is never going to create something this dense. So that little snippet you pull out from beneath the surface, you're looking at like elephant in a teaspoon kind of
Yeah, 15
situations.
tons for a teaspoon.
Yeah, so elephant in a teaspoon scenario. And you're looking at something unbelievably hot, and you're looking at something where the material is arranged so that as it cools it crystallizes.
Hmm.
And this is one of the, to me, most fascinating things about white dwarfs is they start out as like standard plasma that we're used to thinking of our stars as being. But as they cool, they solidify into a crystal structure, and this affects how they cool. So it was originally thought that we could just very, very easily use them as if you look at a cluster of stars and you see white dwarfs at this minimum temperature, that is diagnostic of the most massive stars to become white dwarfs have already had a chance to cool to this point. Therefore, this system of stars is this age. And
Right.
we were finding discontinuities, we were finding weird things, we were finding ages that didn't quite match. And as our chemistry and quantum mechanics got better, it was realized that energy periodically was getting absorbed into the phase changes. And so it was the phase changes of this crystalline matrix that was changing how the star cools over time.
Huh. So I'm just sort of imagining, like, if I, back to that analogy, if I slice out a little piece of my white dwarf, I pull it out, and it's this 10 million degree material.
Yeah.
the mass of the weight of an elephant in my teaspoon or on my little cake knife. I
That
quench
has
it.
melted.
Yeah, of course. Yeah, no, I've got my neutron star cake knife, which is even heavier. I quench it in water, and it will crystallize into what?
Well, this is the awesome part is white dwarfs are generally either helium or carbon, and crystallized carbon is a diamond. So these are objects that when you're looking at a carbon white dwarf star, from the more massive stars to become white dwarfs, um, you're ending up with a solar mass diamond.
Right.
That, to be fair, if you tried to stand upon it to put your hand against it
Yeah.
to pretend you were wearing it, would crush you to
Sure.
its surface and destroy you.
Right. Right. But
Don't try to wear one.
and so at the beginning, at the hot point, it is just this very hot
Plasma.
plasma, but formed into a very tight ball.
The
And it's
electrons are degenerate, which means they're aligned in specific ways
right.
so that their spins are correctly
Yeah,
up
they're
and down, their
marching.
energy. Yeah.
Yeah, they're marching in perfect order. But
Yes.
but the but then as it cools down, it freezes almost. It crystallizes
Yeah.
into this shape that it had arranged itself, trying to fit into the smallest possible size, and that is a diamond
Yes.
because it's made out of carbon.
Yes.
Whoa.
Now the thing about this to remember is these are the remainders of a lot of different kinds of stars. So not all white dwarfs are identical. You can start off with that. We think 10 is order of the top, but it could even be larger mass, originally formed stars that have undergone massive amounts of mass loss. And so they lived as the hot, bright, not the hottest and brightest, but hot, bright stars hanging out there. They're going to form these carbon white dwarfs. Now, at the same time, those little tiny red dwarfs out there, someday far in the future, after all the rest of the universe has given up the ghost, they're going to finally stop undergoing nuclear reactions. They're undergoing convection. So the
Mm-hmm.
entire star is eventually going to get used up. It's going to become pretty much pure helium. And when this occurs, when they can no longer burn anymore for the lowest mass hydrogen burning stars, they're just going to kind of slow down, shrink down. Again, these stars are very different. They don't undergo all the red giant stuff. They just sort of sit there and go, and I'm done.
So then do
Shrink
you
down.
get like a crystal of helium?
Yeah. And the helium's just going, I'm a noble gas. I don't behave this way.
Right.
So there's no crystallization of the helium.
Right, right. It's not going to lock into a structure in the way that, say, a diamond, the way carbon would.
And this is where it gets so interesting trying to understand the way these things cool over time and to figure out how to accurately use them as what we call cosmic chronographers. Um, to measure the age of various star clusters, we have to go, okay, so the white dwarfs are probably this mass distribution at this point
Right.
in this cluster's evolution. Therefore, when we're looking at this band, all right, the coolest ones here are from, and you have to take all of this into account. If you see an isolated white dwarf, you can't get its mass because it's isolated. It's not in a binary system.
Right.
And so you can't figure out what its cooling history would be. All you can do is look at it and say, well, that one's 10,000 degrees
Right. But you
and
can't
know that
say
it's old.
it's right. So you can't say, okay, I know that because it's 10,000 degrees, then I know that it died 14
billion years
Yeah,
ago.
whatever, before the universe. Okay, so it died a billion years ago.
Fair,
I can
fair.
tell just by looking at the temperature. Like astronomers used to think that, right? That
Yeah.
you could measure the temperature of a white dwarf and that would tell you when it died. But I know that like we look in say globular star clusters and we see the like they count the number of white dwarfs there to tell them how old the cluster itself is
And
overall.
And this is where it gets so cool with clusters of stars. Because in a cluster, those 10 solar mass stars had to have existed. They're the ones that will have evolved first. So they're the ones that have been cooling the longest. So when you have a not isolated, because it's in a cluster versus being in a binary, two different ways to be isolated. If you have a white dwarf in a cluster of stars, you can look at this stripe of all the different temperatures that white dwarfs come in. The ones that are still hot? Those are from smaller stars that took longer to
Right.
exhale their atmosphere.
Huh.
And you look at the coldest and you go, those are from the most massive stars.
That did it very quickly.
And so this is a trickstery way to get at the
Wow.
mass. It's just when you see one hanging out by itself that you can't do much with.
Right. It's only when you have them in a cluster that you can actually use them as a diagnostic tool like this.
Yes.
So then let's sort of roll the clock forward. I mean, what is the coolest, like how cool have white dwarfs gotten this far into the universe?
We're still seeing them in the tens of thousands degrees for the most part. They do occasionally get down to like 4,000 Kelvin, 6,000 Kelvin, but for the most part, we're looking at objects that are roughly Earth sized, that are roughly zero point 0.6 to zero point 0.8 solar masses, and they're hot, hanging out in the centers of planetary nebulas, being a source of light to illuminate those planetary nebulas that we're looking at. But that's going to change over time. And this is where white dwarfs, when they were first discovered, really kind of broke the brains of the researchers that were looking at them. And it was Pickering at Harvard College Observatory that got people to take spectra of these dwarf companions of a myriad of different binary systems and realize that something weird is going on because they saw red dwarf, red dwarf, red dwarf. What is this? Because it was known that it had to be small because it was super faint, small surface area. But then the color was that of an A star, something that should be massive.
Right.
So they realized there had to be something new. And these discoveries predated Chandrasekhar figuring out what a white dwarf should be just from doing the maths, which he did while sailing from India to graduate school.
Right. Right. Yeah, what
So
did
he
you
got a
do on
Nobel
your
Prize for that.
Yeah, what did you do on your vacation? He got a Nobel Prize. I
Yeah,
just I
I can tell you what I did. I did not get a Nobel Prize for it. Other people did, but I did not.
Oh, okay. Oh, the I just looked it up. The coolest white dwarf that we know about is about 3,000 Kelvin.
So we're finding them down at the thousands,
Yeah,
but
yeah,
your average one is going to be tens of thousands of degrees.
right. Yeah, this one's probably 11 billion years old.
Yeah, so it's had a chance to cool.
Yeah. And so
And
and so astronomers were able to, I mean, I love this idea, right? That they find something super weird. They find this star that is as bright, that has the color of a of the hottest, most powerful stars out there, but clearly is teeny, teeny, tiny. And then Chandrasekhar says, "Hey, here's a way a star could form that does that."
and one of the things that Chandrasekhar did in beautifully clean math, and if you go through enough used bookstores, you can find Chandrasekhar's Penguin House published Stellar Atmospheres book. And what he'd been looking at is the dichotomy between gravitational pressure pushing in and light pressure pushing out, and what happens at different phases in a star where you don't have enough light pressure pushing out. And that's where you start to get at these white dwarfs and the famous Chandrasekhar limit, where if you put too much mass on a white dwarf, the electrons go, I can't, man. I can't.
Kaboom.
Yeah, and those electrons and the protons that they're associated with come together. There's a tremendous release of energy, neutrinos, other stuff. And what's left behind is a neutron degenerate gas, a neutron star.
So we've got there's sort of like two sides to this, right? We've got the white dwarf
Yeah.
at the beginning, but we've got the concept, the theoretical idea of the black dwarf as well.
Yes.
So what is that?
So a black dwarf is basically an object that is cold, it is tiny, it is the black ember of our universe. It is something you might only be able to see in the infrared initially, but given the fullness of time and luck avoiding black holes, our universe is going to be littered with these extraordinarily dense objects that will eventually cool down to the background temperature of our universe. And this also is provided that protons don't actually decay, which is a concern we have. But given no proton decay, given the fullness of time and not getting eaten up by a black hole, our universe is going to be littered with crystallized, no longer radiating temperature on their own, blobs of helium and carbon. And that's kind of fantastical to imagine. Something like 95% of stars are thought to eventually evolve into these white
Right.
dwarfs that can become black dwarfs.
Right. And so I'm looking at some numbers here like trillions of years, quadrillions of years. You know, some people are talking maybe 10 to the power of 25
This is where I like to
years
just say, in the fullness of
in
time,
the long,
give an escape from other problems.
yeah, in the far, far, far future.
Yeah.
And so I'm just sort of I'm trying to wrap my head around that future. You've got all the stars that have ever lived that didn't explode a supernova and didn't gather
Mhm.
up more material, cooled from red dwarfs to larger stars, even larger stars than our sun, turned into some flavor of a white dwarf, and then cooled down to become
The background temperature.
their
They're giant marbles.
their
That's what
crystal
they
yeah their
are.
crystalline version of whatever they would become. Diamonds, a solid block of helium, other potentially elements, some thin atmosphere maybe surrounding them.
And and white dwarfs, they, because they come in so many different masses, they do have weird different behaviors. Some of the lowest mass white dwarfs will, as they're working on collapsing down under gravity, their outer atmosphere is like, wait, I'm still going to try and do some more burning here. Wait, trying to do fusion. Um, and they also have this neat way of, you can see the imprint of things chemically that go splat on them on their surface later.
Right, right.
So there has been a white dwarf discovered that appears to have consumed a rocky world that lost its atmosphere during the star's red giant phase. When you see one of these, because it's supposed to be just the pure core of a star, you don't expect any heavy elements. Those would have sunk to the very center. And so we're looking at the outer part of that core. There should not be stuff and things, by which I mean heavy metals,
Yeah.
on the outside of a core of a star. And so we can see, well, that white dwarf ate its solar system. And that's just kind of cool.
Yeah, that's amazing that can be seen. You can see the imprint, the bug splatter of the planets as they fell one by one onto the surface of the white dwarf. And in fact, we don't have a lot of time, but I know that a planet has recently been discovered orbiting a white dwarf.
Yes, and this gives us some hope for our own solar system. We understand that our particular future involves the sun bloating out, eating Mercury, Venus, probably not Earth. We think it'll
Actually,
lose enough mass that we're
apparently,
fine.
Phil just posted Bad Astronomy today that apparently the sun will eat the Earth. So that's
Okay.
that's the science today, as of September 25th, 2020. The sun will eat the Earth.
But as of yesterday, we were still
yeah,
good.
it was the other way around. But before
So
that, it was back the other way.
we don't fully know. Anyways, some number of inner worlds will be eaten. Jupiter and Saturn should be fine. And as the sun puffs off its outer atmosphere, this is going to create all sorts of weird physics. It's going to potentially create a situation where the outer planets can migrate inwards. It's going to potentially blast off the outer layers of these planets. We don't fully understand what's going to happen, but what we do know is we have now found exactly one white dwarf that has a gas giant snuggled up next to it in a 30-something hour orbit. And what's kind of amazing about this system is it's thought that the star is about 4 Earth diameters and the planet is order of 10 Earth diameters.
So the
So the
planet's bigger than the
planet,
star.
yeah,
Yeah, yeah.
it's a cool system.
And theoretically, I mean, these things are still putting out heat, and it's a very stable. There's
Yes.
no solar flares anymore. There's no coronal mass ejections. There's no solar wind. There's just light coming from your star for trillions, quadrillions of years as you just snuggle up closer and closer to the star. And so you can imagine some far, far
Endor.
future. Hmm?
You can imagine Endor.
Yeah, you can imagine some future where you take your planet and you just huddle it up beside your white dwarf, and you've got a nice, dependable source of light and heat for effectively ever, and without all
And
that testy solar flares and stuff.
and this is where I think we're more likely to find habitable moons in these kinds of situations
Yeah,
because the gas giant would potentially have the ability to grab onto things as they flew by. It would potentially have the ability to have already had Ganymede-like moons that have all the stuff necessary for life. Um,
yeah,
there's so many cool
yeah.
possibilities.
Well, and next week we're going to talk about how they explode.
Yeah,
So,
things need to explode.
do you have some names for us?
I do. So as always, we are here because of you. We do this because we love talking to you, finding out more, finding out what you're curious about. But at the end of the day, Fraser and I are lazy, and it takes other humans to maintain our website and edit our audio and post our video.
Or busy.
Well, that too. That too. So your donations allow us to pay the people behind the scenes that keep us going, to pay Rich, to pay Allie, to pay our servers, because they like electrons. So I would like this week to thank Paul Jarman, Joss Cunningham, Corey Diwali, Emily Patterson, Adam Anise Brown, Infinitesimal Ripple in Spacetime, Ed Love Science, Gordon Dewey, Bill Hamilton, Sinai, Joshua Pearson, Frank Trippin, Richard Riviera, Jack Mudge, Alexis, Tomit Sepstrup, Sylvan Westby, William Andrews, Jeff Collins, Merrick Vidarni, Ben Floss, Stephen Shewater, Arctic Fox, Nate Detweiler, Dave Lackey, Matt Rucker, Elad Avron, and Philip Walker. And Elad, I'm sorry. I know it's Elad. I always say it wrong. I am sorry. Elad Avron.
Thank you, everybody, and we'll see you all next week. Thanks,
Bye-bye.
Pamela. And then they saved. And of course, Ilad Avron just showed up late to the show. So I think that's the punishment that he gets, is to have his name mispronounced.
I
I hope you've learned your terrible lesson.
so when people take the time and have the patience to attempt to get me to pronounce their names correctly, I try. I try. And when his face is in front of me, I get it right more often than not. But when the spelling is in front of me, I'm just hopeless.
All right, let me just finish saving, and then we will get on to the second half of this show.
Yeah.
Okay. Earlier into the chat, Trey, where was it here? Trey was wondering why there was a 2-week delay from when we do the Astronomy Cast episode on YouTube to when it goes out on the podcast feed. And that shouldn't be happening.
Yeah,
So,
so
Trey
it should
Harmon,
be a
yeah.
4-day delay.
That's right.
So the first episode of the season, we screwed up. Like the audio got posted on Libsyn, and I forgot to remind our website producer that
Okay. So is
that
that
she needed to. Yeah,
right?
I just forgot to remind her, and there was a Monday that happened, and
Okay.
then the
All right.
next week there was a moment of
So it
fix.
might have been like one week where
Yeah,
it was a late delay,
yeah,
but
our first week
yeah,
was fail.
but the system should be we release the episode, we record the show live on Friday, and then the episode goes out on the podcast feed on the Monday. And
Hmm.
so if that's not happening, please
I
let
will
us
look
know.
into it.
Yeah, please let
Yeah,
us know. Like if that's not your experience and not just that one week, but like every week, then absolutely.
yeah.
Stuart Foreman, member of the Virtual Star Party, asks, "What's your favorite planetary nebula?"
Owl.
Owl's pretty great. I like the blue snowball.
So for me, the owl is that perfect combination of really hard to image well, but still looks like something if you have a giant enough Dobson.
Right, right. And so you do get those two little circles for its eyes.
Yeah.
Yeah. And I love the blue snowball. It looks like I'm looking at Neptune. Like it's this blue, this bright blue sphere just floating in space. But I mean, I'm sure we both of us our first planetary nebula is the Ring Nebula.
Yeah, of course.
Yeah, which is such a wonderful nebula, but
Yeah. One of my sadnesses in graduate school was when I first started teaching astronomy lab. It was possible to, if they didn't have the football stadium lights on, to see the Ring Nebula. But by my last year, the city of Austin had grown so much that it was lost to the city lights.
oh,
Yeah.
that's terrible. The like whenever I've used like looked at the Ring Nebula with the telescope, you just see the ring, just see the little ring, like a little smoke ring.
Yeah.
Um, and when you take a picture with like something like this, then you get that beautiful green color in the
Hmm.
center, but you never see it with your eyes. But we were when we were doing the star party in when we went to California, when we actually used, remember that there was like a 22-inch Dobsonian telescope that
Yeah.
somebody had set up,
Yeah.
and you'd climb up the step ladder and look through the eyepiece, and what do you know? You can
It was
actually
color.
see the color of the Ring Nebula. So, whenever people talk about getting those gigantic Dobsonians, I
This
try to
is
talk them
why.
out of it, but then I also say, but they are kind of amazing for a few things.
Yeah.
Like it's only when you go like to get a 10-inch Dobsonian makes almost no difference from an 8-inch Dobsonian. Makes almost no difference from a 12-inch. Like get to 8-inch
6 to 12,
Dobsonian.
you'll notice.
Oh sure, yeah. But if
Yeah.
you get like a 6-inch Dobsonian is a perfectly acceptable Dobsonian
Hmm.
telescope for 99% of people out
Yeah.
there. That you will see rings of Saturn, the bands across Jupiter, the red spot, the poles on Mars, the beautiful craters on the moon. It's lightweight and it's relatively inexpensive, and
Yeah.
you can throw it around, and it's a great machine. And if you spend an extra, if you double your money and you go up to the 8-inch, not much. And if you double your money again and you go up to a 10-inch or 12-inch, not great.
Yeah. The
But
10-inch is the max I can possibly carry. A 6-inch means you can have a backpack over your shoulder and still carry your telescope.
yeah, exactly. So I really try to, because people, they want to see the stuff that they see in the pictures, and you will
Yeah, and you
never
can't.
see that. You'll never see it unless you take a picture.
Yeah.
You've got to switch to astrophotography if you want to see the kinds of pictures, the kinds of images that you're seeing in on Universe Today and during the star parties. That's photography. But
Yeah.
but it does wrap around again when you get to 20 plus inch telescopes, because now suddenly, you know, there's the moons of Mars. Oh,
Yeah.
there's there's the spiral structure in M51. Like it's kind of amazing. Whoa. Anti-gravity nonsense asks, can two black dwarfs orbiting each other reignite into a new star? Or, I don't know.
Yes,
But is that a
it's
question
a
for
thing.
next week? Isn't that an exploding?
It is.
'Cause-
Well, they don't always explode. They can actually combine and form a new star, and it's a thing. We'll discuss it next week.
yeah. Yeah. Okay. Sounds good. Or the week after that, where we talk about other kinds of novae.
Yeah,
Uncle Will is asking, would white dwarfs be perfect spheres or would they be oblate?
they are perfect spheres.
Okay. Let's see. And so a couple people were asking, so Hal McKinney asks, how can a diamond weigh so much and still retain the properties of a diamond? So is it more than a diamond?
So, the definition of a diamond is the structure that the carbon takes on. And this is a compressed version of that structure.
So it's more diamond than diamond.
Yeah, yeah.
Right. But but at the end of the day, like
It's the structure
like
that defines it.
like diamonds produced by the processes here on
Mhm.
Earth to put them under high pressure, they're still a mess
Yeah,
compared to the perfection of these degenerate
yeah,
stellar objects. And Gordon is asking, if you took a teaspoon of material out of the white dwarf, would it expand?
yes.
Well, while it's hot, but after it's cooled and you
Well, so
sawed out a
so
chunk of your
this
white
this
dwarf.
is this is actually the really cool thing that probably should have come up during the episode. The radius of white dwarfs is inversely proportional to their mass. So the more mass you put on them, the smaller they get because the electrons are like, ah, and they just are getting closer and closer and closer. So if you remove it, it's going to have less gravitational pressure. The electrons have a little easier of a time pushing each other apart, and it's going to expand out ever so slightly.
Right. Lillian Brennan is asking, is this because of the longer exposure, astrophotography versus looking through a telescope? So,
Yes.
so
It also has to do with rods versus cones in your eyeballs.
right. So
Um,
meat camera versus silicon camera.
Yeah, so the meat camera is most sensitive to light, no light with your peripheral vision. Your central vision is where the color is located. And the detectors are going, is this reds? Is this greens? And because it's filtering, it takes a lot more light to trigger the color response. Just like in a color camera, you have to do longer exposures than in a black and white camera. So the outer part of your vision, which goes light, no light, is like, I've got this. I shall
Right.
show you this
Yeah.
planetary nebula.
Right.
And your color vision is like, nope, not
Yeah.
can't.
It is kind of amazing to do that when you look through the telescope and you use your peripheral vision in a way that there's no other time that you do this. But
Comet finding.
no, but just in general, like I'm
Yeah,
saying,
yeah,
like
yeah.
in your regular life, you will never experience a time where your peripheral vision, you're going back and forth between peripheral and central vision
Yeah.
to find things. But you do this with astronomy, that you look around in the eyepiece, use your peripheral vision to spot things that are faint, and then see if you can actually zoom in on them with your eyes.
And this is a fabulous evolutionary adaptation because once upon a time you were much more worried about things coming out of your peripheral vision to try and eat you in low light situations.
Right.
And so we had to have more sensitive peripheral vision, and it just leads to really weird skills for amateur astronomers.
John Suffield is saying it's a Newtonian telescope on a Dobsonian mount. No such thing as a Dobsonian telescope. Fine.
Fair,
Fair.
fair.
Okay.
We agree.
Gordon Dewis is saying that averted vision is a trick that pilots use to find other airplanes while flying. Oh, interesting. Yeah. So same thing.
Okay.
Yeah. That you're, I guess, looking around the sky using your averted vision to find things on a close approach. That's really interesting. Hal McKinney and Paul Disney have some questions about neutrinos. So, Paul Disney asks, do neutrinos have mass? Do they
Yes.
go the speed of light?
No.
Okay. And then Hal McKinney wants to know, do you think the speed distribution, what is the speed distribution of neutrinos? Do they all go the same speed or do they go different
No.
speeds?
Yes. So
Huh.
neutrinos have the fascinating capacity to exchange their mass into their kinetic energy. And so as they switch flavors in their motion, their velocity, their speed will their kinetic energy and their mass energy, that total number is conserved. So as they change flavors and as they change mass in the process, their kinetic energy has to change in
Whoa.
the process. So the velocities vary and the masses vary.
And this was the big discovery. This was the big amazing discovery about neutrinos was that they
They
change
change
flavor
flavors.
in transit.
Yeah.
And
And
so,
this solved the reason why the sun wasn't producing the number of, I think it was electron neutrinos that we were expecting. It's producing them. They just aren't the same thing by the time they get to the planet Earth.
right, that they're actually just changing
Identity.
their identity, yeah, in flight,
Yeah.
in time.
Yeah.
And so suddenly you're receiving the wrong, they were not able to detect the kinds of neutrinos that they were turning into. And then when they were able to finally have a more sensitive instrument, they could start detecting those and realize that they were going from one kind of neutrino to another. Amazing.
So my favorite thing about this is in order to have less mass, to weigh less if you're in a gravitational field, they have to move faster. So the fact that runners weigh less is just an analogy to how neutrinos behave. The slower moving ones are the fat ones.
Right. Paul Dizzy is asking, would light be able to pass through white dwarf material, assuming it was cooled down?
Um,
Like a
depends on the
slice.
wavelength.
Like a slice. Like say you took
Like I can imagine gamma rays and X-rays. I don't know at what color they become. It becomes opaque though.
but if it's diamond, like light goes through diamond. So if you just like
Well,
sliced off a chunk of white dwarf,
so it's going to depend on the thickness because if
right,
you have a thick enough diamond, the light's just not going to make it
right,
all the way through.
yeah, yeah,
So it depends on the thickness and the wavelength of the light.
right. Yeah, I mean anything. I mean you have water, even though water is transparent to visible light,
Yeah,
thick enough, and it's not anymore.
yeah.
Nicholas B is asking, speaking of astrophotography, I need a portable platform to put my telescope on that can be leveled easily. Any suggestions? I'm tired of dealing with soft ground.
Um, I mean, ultimately, take a piece of plywood and have a tripod with adjustable legs.
Yeah.
It's a lame solution, but it's cheap and practical.
Mm-hmm.
There's some really good leveling tripods out there. A lot of people will also get they're made for this purpose. These rubber discs that are lowest in the center that you put underneath each of your tripod pod legs and it distributes the weight.
I'm kind of imagining, because telescopes are so heavy, like this
Yeah.
this telescope is 80 pounds, and the you put it down, and then on the soft ground, it's going to slowly sink its legs in, and every just millimeter of drift is going to wreck your
Yeah, this
photographs.
is why you get the big old
Yeah,
rubber things drop me an email, plg@psi.edu, and I'll send you recommendations.
right on. There you go. So this, of course, this exists. It's out there.
Yeah.
Someone's had the same problem as you, and someone will be able to figure it out. So that's very
Yeah.
cool. All right, well, we've reached the end of our hour. So thank you everyone for watching with us. Thank you to all of the moderators who were jumping in to help with the comments. Thanks as always to my co-host, Dr. Pamela Gay. Always a pleasure, and we'll see all of you next week. Thanks, everybody.
Bye-bye.
Gives me a hard time if I press that button. I'm going to press this button.